Okay, chapter 2.1. Here we're going to begin chapter 2, where we're going to talk about derivatives, different ways to calculate a derivative without using first principles. In fact, shortcuts. Okay, let's start with the constant. A constant function. Let's look at this one. F of x equals 6. So what do we know about f of x equals 6? Well, it's a horizontal line, right? So if I sketch out a horizontal line at 6, okay, and I can look at any point on this line, right? It's a straight horizontal line. So what really is the tangent? No matter where you go, it's always the same slope. The slope is 0, right? Slope of 0. So the derivative, we can see it intuitively here. The derivative, which is the slope of the tangent, at any point on this line is going to be 0. Okay, so that's our first rule, right? A derivative of constant is 0. Now, do we need proof for that? We can always look at the first principles definition of a derivative to show that, right? So if your function is defined as f of x equals some constant c, any constant c, okay, we can show that the derivative f prime x equals 0. How do you do that? Well, what is f of x plus h? If the input is x plus h, it doesn't matter what the input is. The output is c. So here we have c. F of x, the output is c. C minus c is 0. Okay, 0 over h is still 0. All right, and I could do that, right? I haven't applied the limit yet. I still have the limit notation out here. And so now I simplified the argument here for the limit is 0. So now when I apply h equals 0 here, I can do that, and the result is still 0. There's no h there anymore, so the result is still 0. And so the derivative of a constant is 0. Okay. That's the first rule. It's called the constant rule. The second rule I'm going to introduce you, there are many rules in this chapter, but I'm going to introduce you this second one here for this lesson today. The derivative of a power function. You remember power functions, right? These are functions where f of x equals some x to the power of some integer n, okay? And the derivative of this one looks like this. The derivative of f prime x equals n times x to the power of n minus 1. What does that mean? Now, we did do some derivatives in the first chapter, but I'll challenge you to do them again, right? If I give you these functions, so here's f of x, right? Find its derivative using first principles. So a little chart, right? Try to find the derivative of x squared, okay? Find the derivative of x cubed. Find the derivative of x to the power 4. Find the derivative of x to the power 5, right? Pause the video, take the time, try doing these derivatives using the first principles definition of the derivative. Okay, and what I mean by that, if you forget, what do I mean, right? First principles definition, so f prime x, if I take x squared, for example, is just going to be the limit as h approaches 0 of x plus h squared minus x squared over h. And what does that simplify to? Well, the limit as h approaches 0. And we've done this derivative before, right? So it's going to be x squared plus 2hx plus h squared minus x squared over h. And then we can see x squareds cancel, h's cancel, and you're left with, when I apply the limit of h approaches 0, then I'm just left with 2x. So there's my derivative, 2x. Right? So my derivative function, 2x. Do the same thing for x cubed, x to the 4, x to the 5th. Pause the video, try it. Okay, so hopefully you've done those derivatives now. If you unpause the video, what you should have gotten when you did your work, well, the derivative of x cubed would be 3x squared. The derivative of x to the power 4 would be 4x cubed. And the derivative of x to the power 5 would be 5x to the power 4. And you may recall back in chapter 1, I mentioned something like, well, the derivative, the degree of the derivative is always going to be 1 less than the function, right? So from 2, we go to 1. From 3, we go to 2. 4, we go to 3. 5, we go to 4. And the exponent on the function actually also becomes the coefficient in the derivative, right? 2 is there, 3 is there, 4 is right here as a coefficient, and exponent 5 becomes the coefficient there for the derivative. So there's a pattern to be found here, right? And that pattern is what gives us this, right? Where if you had some function raised to exponent n, the exponent now becomes the coefficient in the derivative, and you just reduce the exponent of the function by 1, and that's the new exponent for the derivative. Okay, so it's 1 degree less. Now that's pattern recognition to getting the rule, right? So, you'd say hey, x to the power of n. If you continue the pattern, it would be n times x to the power of n minus 1. But sometimes it's not satisfactory. You want to kind of get a proof for that. So here's a proof using the first principles definition of a derivative, right? Where we now put in, for f of x plus h, the input is x plus h. But what's the function? A function raised to the power of n. F of x, what's f of x? X to the power of n. So we're going to solve this limit or simplify this limit. How do we do that? Okay, well, a little bit beyond the need to understand this for the scope of this course, but for your understanding, I'll guide you, right? So if you recall things like the difference of squares, right? X squared, let's use a, right? So a squared minus b squared was a minus b times a plus b. Okay, if you did a difference of cubes, a cubed minus b cubed, there's also a formula for that that starts with a minus b, and then there was an extra term there. There's also a formula for a to the power of 4 minus b to the power of 4, right? That starts with a minus b times another long factor there. And there is also a formula where if you have something called the difference of nth power, right? The difference of the nth power. And that's what this is called, the difference of the nth power. And you can look that up, right? And there's a formula for that. And when you expand that, this is what you get. Okay, so I'm not going to require you to know that. I'm not going to ask you to use the first limit definition to prove x to the power of n, but you can certainly look that up if that's your interest. Okay, and we could talk more about it in class once I return. So that's what you get when you do that. And then when you simplify this, you get your h up in the front, which cancels with the h in the denominator. Okay, and you have a series of terms on the inside. Okay, and so the h's are gone in this step. We haven't applied the limit yet. Once you apply the limit, right, things like x plus h to the power of n minus 1 just become x to the power of n minus 1, which has a duplicate at the very end. Okay, but notice how x plus h to the power of n minus 2 times x, when h is 0, it just becomes x to the power of n minus 2 times x, and x has that invisible 1. Okay, and it turns out that every single term in this expansion, right, resolves itself, right? X to the power of n minus 2 times x to the power of 1, multiplication rule of exponents, add their exponents, n minus 2 plus 1 just becomes n minus 1. And this term here, I have an x n minus 1. Every term is going to be that way, except for, actually, addition x minus 1. Okay, and then when you collect all those terms, how many of those terms do you have? Well, you have n of them, right? So it's going to be n times x to the power of n minus 1. Anyways, that's just the proof of the first principles definition of x to the power of n. For our purposes, all we need is just the end result, and the end result is the derivative is n times x to the power of n minus 1. And that's going to save us a lot of headache from having to use the first principles definition over and over and over and over and over again for other different power functions. We now have a rule that we can follow called the power rule. So if f of x equals x to the power of n, then its derivative is n times x to the power of n minus 1. Okay, so determine the derivative of the following. X to the power of 5, its derivative would just be bring the exponent to the front times x, reduce the exponent by 1, make that a 4. 5x to the power of 4. For f of x equals x to the power of 7, its derivative, bring the 7 to the front, and then we have x to the power of 6. Right? Could you imagine doing x to the power of 7 using first principles definition of the derivative? Take you a long time. Now we have a rule that makes it simple. Okay, try these questions. So if you tried them, the derivative for the first one, f prime x equals 8 times x to the power of 7. For the next one, you can use a negative, so negative 6 comes to the front, reduce the exponent by 1, it becomes negative 7. Not negative 5, negative 7. So subtract 1. Okay, and so that's the derivative for that one. Okay, now what if we have a constant in front of the function, right? So if a function f of x equals 5 times x to the 7, and 5 is a constant, and then multiple of a constant multiple of a function x to the power of 7. The derivative of a constant times another function is equal to the constant times the derivative of the function. Meaning, if f of x equals to constant times a function, like a power function, then the derivative is the same constant times the derivative of the power function. Okay, and so here's the proof. Right? So you take the function, the limit as h approaches 0 of q of x plus h minus q of x, multiply that by a constant in the front. What happens? Well, you can use your limit properties. You can factor out that constant, and then you can bring that constant outside the limit. Okay? And then everything else you see here, this is just the limit definition of a derivative if the function is q of x. And so that can be now replaced with q prime of x. That's a pretty simple proof for a simple kind of derivative rule. All right, so how does it apply? So here's the same set of here's a function, 5x to the power of 5. Its derivative is just, hey, put the 5, keep the 5, and then take the derivative of x to the power of 5, right? What's the derivative of x to the power of 5? Well, it'll be 5. The 5 goes in front of the x, and then reduce the exponent by 1. Okay? And then you simplify. So 5 times 5 is 25. So 25 times x to the power of 4. Same thing. So same idea for the next one. F of x equals 7 times x to the power of negative 7. Its derivative, f prime x, well, you keep the constant, 7. Take the derivative of the power function, negative 7 times x to the power of, reduce the exponent by 1, negative 8. And then you simplify. You get 7 times 7 is negative 49 times x to the power of negative 8. Okay. All right. Sum or difference of terms. So what if you have a function that is sum of two other functions, sum of two terms? Okay. Its derivative is the derivative of each term. Pretty simple, that one is. Okay. So the proof, here it is. So what if your function f of x is composed of two functions, p plus q? Okay. So that's what it looks like if your input is x plus h. And what if it's just f of x? So here it is, p of x, q of x. Right? You're subtracting them, so you have to subtract these subtraction signs. And then if you reorder them, right? So here's p and p. Put them together, p and p. Q of x plus h and q of x, put them together, q of x plus h minus q of x. Just reorder them. Why do I want to reorder them? So I can expose two separate limit definitions of the derivative. And then using limit properties, I can separate these two as the sum of two limits. Okay, and each limit represents its own derivative p prime x, and the second one is q prime x. Okay, so as an example, you're given a polynomial. Each term in a polynomial is a power function. Can I find its derivative? You certainly can. F prime x starts with the derivative of 4x cubed. Okay, so what you can do here is multiply the exponent directly with the 4. So 4 times 3 is 12. Write down the x, reduce the exponent by 1. That's 2. Okay. Well, if you don't see what I did there, what I'm saying is this. Well, what's the derivative of a constant times a power function? You just keep the constant, take the derivative of x cubed, which was 3x squared, right? And we know that's going to be 12x squared. I just kind of skipped the step at this point. Okay. But you can, if I don't skip the steps, well, look, constant is 3. Derivative of x squared is 2x. Okay. And the derivative of 5, well, 5 is a constant. So that derivative of a constant we already established was 0. Okay. And so if I simplify this, 3 times 2x is 6x. There's my derivative. Okay. So remember what does the derivative give you? It gives you the slope of the tangent to f of x at any point x. So if I wanted to know the slope of the tangent at x equals -1, plug it in. F prime of -1 is 12 times -1 squared plus 6 times -1, and that's going to equal 6. So the slope of a tangent line for this function, this cubic function, at x equals -1 is 6. Okay? What's the whole equation for the tangent line? Well, you got to use the equation of a line. Y equals mx plus b. And I'm also going to start to introduce you to this other form of the equation of a line, right? So if you're familiar with the slope formula, right? M equals y2 minus y1 over x2 minus x1. Okay, what if I rearrange this formula to say, hey, m times x2 minus x1 equals y2 minus y1. So all I've done is just multiply both sides by x2 minus x1 so I can get rid of a denominator, right? Okay, and so I could apply that formula as well and just change it slightly. What if I said m times x minus x0 and y minus y0, which is more commonly how this formula is given. So you can use y equals mx plus b, or you can use this formula, and actually the formula is actually even furthermore written with the y on the left side, like so. But let me show you both ways. So if I find the equation of the tangent line using y equals mx plus b, then I'm putting the slope as 6, right? So y equals 6x plus b. Do I know a point on this line? On f of x? Well, I have to find it, right? So what is f of -1? Well, that's going to be 4 times -1 cubed plus 3 times -1 squared plus 5. And that's going to be -4 plus 3 is -1 plus 5 is 4. Okay, so the coordinate -1 and 4 is both on f of x, and it's also on the derivative f prime x, right? Because remember I should be more specific. The derivative at -1, right? Actually, let me correct myself. It's on the tangent line. I should be saying the tangent line of f of x. Sometimes I need to visualize this, right? So if you have a cubic function and you have a point at -1, okay, and you have a tangent line. Whoop. So that point we found, -1 and 4, that's a point on the function f of x. but that's also a common point on the tangent line, on the green line, okay? So I got to use that point to find the equation of my line. So here it is. 4 equals 6 times negative 1 plus b. Solving for b, we get b equals 10. And so the equation of my tangent line is y equals 6x plus 10. Now, if you know this form of the equation, it's pretty simple. Y, you keep y as y, subtract the known points. The y coordinate of the known point is 4, so I subtract 4. I know the slope is 6, so I put m is 6. Keep x as x, and you subtract the x coordinate that's on this, that we know from this line, which is negative 1. And then we simplify y equals, if I distribute this, so 6x, 6 times, so double negative makes positive, so plus 6. Bring the 4 over to the other side, I get plus 4. And so y equals 6x plus 10. Same answer. Maybe you might think this is nicer to work it out on this way, in this fashion. And I'm going to repeat this over and over again as we progress, right? Okay, try this question. Determine an equation for the tangent to the curve. Pause the video, try it, come back. Okay, hopefully you had a chance to try it. Let's present the solution. Start with the derivative. We can use the notation y prime because we're given y. So the derivative is power rule. 3 comes to the front, 3x squared, okay? Minus, what's the derivative of x squared? Well, 2 comes to the front. It'll be 2x. 2x times 3 is 6x, okay? Derivative of minus 4x. Well, if the exponent is 1, 1 comes to the front. Multiply it with the 4, you get minus 4. Reduce the exponent by 1, so 1 becomes a 0. X to the power of 0 is just 1. Oh, well, I don't need an x anymore. It's just minus 4. Okay? Derivative of 1. It's a constant. It's 0. Do I put a plus 0? You could, but you don't need to, right? We don't usually put the plus 0 at the end if you have other terms there. So we're good. That's my derivative, right? It's the degree of my derivative is 1 less than the degree of the function, which works. Okay, so there we go. And again, what does the derivative tell you? It tells me the slope of the tangent line at any x point. So if I want to know the slope at x equals 1, all I got to do is plug in my input of 1. F prime of 1 is equal to 3 times 1 squared minus 6 times 1 minus 4. And that's going to equal, let's be proper here, 3 minus 6 is negative 3, minus 4 is negative 7. So there's my slope. That's my slope of the tangent. Okay. What's the equation of the line? Well, I need to know a point on the line. Okay. So if I know x equals 1 is on the line, what's the corresponding y value? Plug it into the original function. F of 1 equals 1 cubed minus 3 times 1 squared minus 4 times 1 plus 1 equals 1 minus 3 is negative 2, minus 4 is negative 6, plus 1 is negative 5. So the point that we know of is 1 and negative 5. Plug it into the function for the equation of a line. Okay, so again, you can use y equals mx plus b, knowing the y coordinate is negative 5. What is our slope? We said the slope was negative 7. What's the x coordinate? 1 plus b. Solve for b. We get b equals 2. Okay, and so the equation of my tangent line is y equals negative 7x plus 2. Okay, or you can use the other form of the equation of a line. Here it is, y minus y0 equals m times x minus x0. Y is y as your variable. Y0 is the known point on the line, so y minus negative 5 equals the slope, negative 7, times x is x. Take away the known x coordinate, take away 1. And you simplify, right? Y equals distribute negative 7x. Negative 7 times negative 1 is positive 7. Minus minus 5 makes plus 5. Bring it over to the other side. It becomes minus 5. And here's your equation of a line. Minus 7x plus 2. Same answer. But I like doing it this way because it seems much faster and easier. I mean, pretty much the same number of steps, but you could shorten the number of steps here too. All right, let's look at another example. Determine the points on the graph of, well, let's erase this, of y equals x squared plus x times x plus 3, where the slope of the tangent is 24. Ah, interesting problem. Okay. How do I find, well, the slope of the tangent is 24. If I said f prime x equals 24, what is x? Okay, so I need the derivative, right? So f of x equals x squared times x plus 3. But how do I do that, right? This is not a power function. This is not a constant. This is not a addition of functions here, right? This is a function times, this is a function multiplied by another function. We don't have a rule for that yet. Well, that rule is coming up soon. So for now, what you should just do is expand. X squared times x is x cubed. X squared times 3 is 3x squared. And now I have a function that is a sum of two functions, two power functions. Okay, so this is f of x. Derivative f prime x is going to be, well, the derivative of x cubed using the power rule. Just bring the exponent to the front, 3 times x, reduce the exponent by 1, so 3x squared. Okay, so that's this one. Derivative of 3x squared, right? Bring the 2 to the front. 2 times 3 is 6. Write down the x, reduce the exponent by 1, so 2 becomes a 1. Or you could just say 6x. Okay, so there's my derivative. So at what value of x does my derivative equal 24? Because the slope of the tangent is 24. So 24 equals 3x squared plus 6x. What value of x does that occur? Solve for x. So if I factor out of 3x and then an x plus 2, I'm going to have, silly me. Make one, when you're solving an equation, make one side 0, right? So 3x squared plus 6x minus 24. Okay, solve this. Can I factor out something? Yes, I can factor out a 3. So 3x squared plus 2x minus 8. Is x squared plus 2x minus 8 factorable? It is. So 0 equals 3 times x plus 4 times x minus 2. And so I have two solutions. X equals negative 4 and x equals 2. This means the derivative f prime at negative 4 is equal to 24, and f prime at 2 is equal to 24 as well, right? The slope of the tangent at negative 4 and at positive 2 is the same slope. How can that be? You might wonder. You want to find out? Let's find out. Okay, so let's see. Yes, so here, now you can see, okay, so here I've just put a copy image from Desmos, and what you see here is in red, you have the function f of x, right? And here are the points. At 2 and at negative 4, you have these two tangent lines, and they're parallel to each other, and they have a slope of 24. Okay, so it's possible to have more than one solution. You can have a tangent line that has the same slope as another tangent line somewhere else, and that's possible. Okay, if there are any domain restrictions, then maybe I wouldn't include one of these solutions, perhaps. right? But there are no domain restrictions. Any x value is valid. So we found 2 of them. Okay, so that's that question. Why don't you try this one, right? Determine where the slope of the tangent is 0. So, cubic function, you want to know, like, hey, is a cubic function, what x values do I have a tangent of 0? You might have 2 possible answers here too, or maybe not, right? It depends. Okay, so let's give you a chance to do that one, and we'll come back to class and answer any questions from the homework. All right, so that's it for this lesson. See you in the next one.